Thanks for watching. Please like, share, and subscribe. And please look in the description beneath this video for useful links to other videos and resources to help you learn chemistry. For today's video, I'm going to teach you how to answer the question shown here. I invite you to pause the video right now and try this question on your own first, then hit play and I'll show you how to do it.
So an ideal gas is a theoretical gas whose behavior can be perfectly predicted by the ideal gas law. So in real life, most gases behave pretty much like ideal gases. That is, they behave ideally within a certain range of temperatures and pressures. And just so you know, gases generally behave ideally at high temperature and low pressure. Now, in order for gases to behave ideally, that is, like ideal gases, there are three things that they must do. We call these the three assumptions of an ideal gas. And please keep in mind that these assumptions are made to simplify our understanding of gases, and they are not always true in real life. However, they are generally true enough, especially at high temperature and low pressure, to make reasonable predictions of gas behavior. Those assumptions are as follows. First, the volume or size of each individual gas molecule is insignificant. That is, an individual gas molecule itself is pretty much infinitely small when compared to the relatively massive volume occupied by all of the gas molecules in a sample collectively. Second, gas molecules' collisions with each other are perfectly elastic. That is, they collide and rebound off each other without sticking, and therefore do not experience any intermolecular forces with each other or with the inside of their container. And third, the average kinetic energy, or EK, of a gas depends only on the system's temperature, not on the gas identity or the size of the gas molecules. In other words, we could say that as temperature goes up, kinetic energy also goes up. And that should make sense as you think about it, because if you warm up a system, the molecules move around faster and faster and have more kinetic energy. In fact, this relationship is so important for a question that I'm going to place it in the top corner here of our next slide. So here is our question. Let's analyze the answer options one at a time, starting with B, which claims that the kinetic energy of gas molecules decreases with increasing temperature. Does that seem correct? No, as we just pointed out, it's the exact opposite. As you increase temperature, you increase kinetic energy, as I've written in the upper right-hand corner, so we can eliminate B. C states that the average speed of gas molecules increases with increasing molecular weight. In other words, it states that as molecules get larger in size, they go faster. Does that logically seem to make sense to you? No, I think it would actually be the opposite. That as a molecule gets larger in size, it moves slower. And that turns out to be the case. These two things are inversely related to each other, and you should definitely make sure you memorize that. Hence, we can eliminate option C. D says that the number of gas molecules in a given volume is directly proportional to the mass of each individual molecule. Does that make sense? Well, as I just pointed out, one of the tenets of ideal gas behavior is that the size of each individual molecule is insignificant relative to the overall collective size of all of the molecules in the gas sample together. Hence, we can eliminate option D. So what of option A? Well, it says that all gases have the same average kinetic energy at a given temperature. In other words, kinetic energy is directly proportional to temperature. And when making ideal gas behavior theoretical assumptions, that ends up holding true for all gases, regardless of their identities. Thus, this question's correct answer is option A.